that didn't work. Hi, I'm Kent. We've been slowly working on my new mold system. The idea is to make a sketch of the outline of the pot, and then the software basically does everything we need to make molds for slip casting. It goes and creates a scaled version like this so we can figure out the form if we like it, scales it up to account for clay shrinkage, adds the slip well, and then most recently I've went ahead and made the software so it creates an outer mold for the plaster and a ring. So the idea is that this needs to be assembled. So this is the inner mold that forms the pot. It goes like this, and then the outer mold goes like this. That all gets attached together, and then we pour plaster in here, and then that gives us a plaster mold like this that we can slip cast into. Since making this, we've addressed a few problems. In the last video, we dealt with the inner mold sticking, basically how to get this piece out here. The other issue I had was it leaked a little bit on the outside. So the wax I tried and the geometry I have for this ring didn't quite work. And then I wound up cutting the outer mold off. Here is the seam I went ahead and cut in. That is less than ideal. In this video, I want to revisit how I'm doing these attachments. So one is I want to revisit how I'm attaching this bottom ring here. I need to think about how I'm going to attach the inner mold to the ring and then the outer mold to the ring. And then I want to eventually go ahead and put in a side seam as well. That way we can break this apart and have it open up and not have to cut it. And potentially we can do this in multiple pieces so we can print this in several pieces as well. In doing so, we have a couple different seams to think about. So one, we have basically this 90-degree seam here. So we have the vertical wall going to the flat part. We also have basically a parallel seam here. So we want these two pieces to be able to seam together and create a joint. So while in the first video I was wondering about how to attach this ring, I realized that I actually have more problems to solve in attaching these 3D printed pieces together. I've been thinking about this for a little while now and realized I actually have a bunch of competing requirements, and that's one of the reasons it's challenging. First, I want to be able to easily assemble this and disassemble it. This only needs to hold back plaster for about half an hour. So if it takes a long time to assemble it, that's a challenge because it feels like wasted effort. Likewise, if it's hard to get apart, that's also a problem. We also need it to be relatively strong. So when this is full of plaster, there's a lot of liquid in here, and the plaster is actually denser than water. So that means it will want to try and find a way to blow this apart. And then finally, we need something that seals tightly. The plaster is very fluid, and if there's a leak, it will find a way. And like I teased at the beginning, I'm going to use water as a proxy and see if we have any leaks in anything we try. Together, being strong and sealing tightly will prevent plaster disasters. I've had a few of those, and I really want to try and avoid them. The flip side of that is those are basically in contradiction to making it easy to remove. So being strong and sealed tightly means that it's going to want to resist being removed. One of the other things in thinking about this is that we want to be able to align the parts. So when I created this ring here, I created this lip. And there's a little bit of a space there so I could get the 3D parts on, but there's relatively little room for it to move around. Similarly for the outside piece, the ring here acts as an alignment. And for this particular part, it doesn't really matter. All of these seams are basically on the outside of the plaster and are not where the pot's formed. However, as we get into multi-part molds, this will become more critical. As I mentioned, we have some different types of geometry. We have this right angle at the bottom, and then we're going to want to be able to seal the sides. And then finally, I want to assume the 3D print isn't perfect. I've been using my 3D printer a lot recently, and slowly I've been tweaking it and getting it dialed in, which is great. The prints are coming out better. However, getting the 3D printer really dialed in is a skill all by itself, and not one I'm particularly interested in. I'd rather just my 3D printed parts come out. And if they aren't coming out perfectly, I'd like to be able to adapt my process to work with that. The other part of that is I want you guys to be able to use this software eventually, which means I can't assume that your 3D printer is going to be perfect. If it is, that's great, but if it's slightly mistuned or producing parts that aren't exactly perfect, then hopefully this will work for you as well. In other words, I don't want a perfect print to be a barrier between you using this software versus not. 3D printers are also inherently limited. So these FDM printers basically squirt out little pieces of molten plastic and fuse it together. And you can make that more and more precise. You can basically slow down the print so it moves more precisely and use smaller nozzles and do smaller layer heights. But at the end of the day, there's still going to be a texture in the print. 3D prints can also warp in a variety of ways due to thermal characteristics and internal stresses. So for instance, they can lift off the bed and warp slightly. Or if you're printing a vertical wall, there might be some wobble that creates some slight offsets. These can be dealt with in post-processing, but again, I'm kind of lazy and I'd rather not have to if I don't need to. And it's not just an issue with FDM printers, these filament printers, it's also an issue with resin printers. Kurt Hammerly recently shared on Instagram that he was having a problem with one of his resin printers. He has two, and they aren't printing the same part exactly the same height. They are off by a fraction of a percentage, and that's actually causing him issues. So even switching to a different technology doesn't necessarily solve all these problems. So how far can we get with good enough prints is really one of the questions I want to try and tackle here, and is basically a requirement as well. So that's a lot of different requirements that we're trying to solve for here. And in the past few videos, there's been a lot of comments, and I really appreciate those. It's great to have an active discussion on these videos, and I really appreciate the new ideas that people are throwing out. In reflecting upon a lot of the suggestions, I've realized that most of them only deal with part of the requirements. And I think that's one of the things that makes this hard. There is maybe one material approach that can solve some of these, like for instance being strong, but it then fails with some of the others. So I think that is why this is actually hard, that we have all these conflicting requirements and they need to all come together in this kind of magic Goldilocks zone. So let's go through some of the options. When I started the deep dive, I actually went to silicone caulking early on. This actually works relatively well. So it acts as a sealant, so I don't have anything leaking, in particular plaster leaking out. It's also relatively strong in that it can hold back the plaster for the time needed. From my perspective, the biggest downside is that this is slow. It takes about a day to cure. And while pottery requires a lot of patience, adding in another step that requires even more patience is not what I'm going for. So if you're okay with kind of the slow, steady approach, or can plan around it, then I think this is actually a pretty good option. Also, when I started my deep dive, I showed my use of caldle boards. These let you build a structure around the outside of your mold. And they have some issues, which is why I went to a 3D print. However, they do have their place. And the idea is that you can actually clamp these together and make it various sizes relatively easily. And the clamp is making it strong. So that's solving one of our problems. The issue is this seam here on the inside isn't watertight, or in particular plaster tight. As a result, you need to add something else inside here. You basically need a sealant. So you can use things like throwing clay or caulking, or I've used tape before. So now we're combining a couple things. The clamps make it strong, and then the clay acts as the sealant. Some people have also suggested using plumber's putty. Basically, this is used in the plumbing industry to make a waterproof joint. And I went looking at it a little bit, and it has some nice advantages. It obviously holds back water. The problem is it's not very structural, kind of like clay. If you pull on it the wrong way, it will let go. And that's the challenge with just using clay to hold things down. So for instance, I've used clay to seal this again, but if you jostle it or things move a little bit, it's not very strong. It can break apart relatively easily. So maybe if you're careful or use it in just the right ways, it works just fine. Similarly, people have suggested rolling out a slab of clay instead of using the bottom ring. You can then press this piece into the clay bed and this piece into that clay bed. And if it's stationary and you have enough clay, I think that would work. However, it only deals with this bottom seam, and it probably wouldn't work for the side, or I'm not sure it would work for the side because this is going to want to pull apart. And I don't think the clay would withstand those stresses well. I've used this foil tape quite a bit. This is meant for ducting in a house for air conditioners. And I think because of that, it's meant to deal with condensation. So basically changes in temperature and water condensing on the metal ductwork, which means the adhesive on this also deals with moisture okay. I'm not too sure I'd want to put it underwater, but in practice, holding back the wet plaster for half an hour while it cures has worked pretty well. The big problem with this is, well, one, the backing is kind of annoying to remove, but it also bites. So this foil is pretty sharp and it gives you really nasty paper cuts. So I think it's a pretty good solution overall, and maybe if you're a little bit more careful than I am, it would actually work really well for you. People have suggested using other tape, like painter's tape. This doesn't have the problem of biting you, it won't give you paper cuts. The problem with this, I think, is that the adhesive isn't strong enough. This is intentionally designed to be removable, so it doesn't take the paint off the walls when you're painting, which means the tact on the tape, the stickiness of the tape, isn't extremely strong. That's great in the removal process, however, we need it to hold together. I think some people have used this successfully, but it feels like we're kind of in the danger zone in terms of maybe it works sometime, but if you do the wrong thing or don't get it pressed down just the right way, it might leak. In putting together this video, I was thinking about some other tapes. So one is the classic duct tape. Mythbusters did a bunch of videos on this showing how versatile it is. It definitely is waterproof. They made a boat out of it. The real problem, I think, is the undoing. It winds up being very sticky, and taking it apart can be tricky. A cousin of duct tape is actually gaffer's tape. So this is used in the film industry and doesn't have the sticky residue problem. It's meant to be removable. Gaffer's tape is actually something I want to try in the future and see if it solves some of these problems. The real trick there is that there might be variations between different types, and getting the tact just right is a little bit of a challenge. All of the tapes have a similar problem in that they don't actually address the alignment issue. So we need some features in the 3D print to deal with alignment. This basically potentially acts as the strength and acts as the sealant. One of the other suggestions is to use hot glue. So the idea would be to go ahead and put down a bead inside of a groove here, and that would act as both the strength and the sealant. Of course, in order to actually seal things, that means I would need to get a constant bead all the way around. I think the challenge with hot glue is removal. So it turns out that isopropyl alcohol will actually dissolve hot glue. So I tried this out off camera, and it does actually do so. It seems to be very slow though. I think the alcohol attacks the glue bonds and eventually will make it not adhere anymore. The problem is you really want the alcohol to go between the 3D print and the hot glue, and that's exactly the part that's sealed. So I think with patience you could actually get the alcohol to work. It just doesn't quite work as fast as I want, and getting the rest of the residual hot glue off I think might be a challenge. This isn't an explicit goal, but it would be nice to be able to reuse these parts multiple times. So for instance, I've already cast 2 sets of plaster out of this mold. So kind of cleanup at the end is part of the removal process. The other problem with hot glue is the type of joint you can seal. So for instance, I would like to be able to put a bead of glue down all around the outside here and then press this in. However, getting the timing of that right with hot glue is a little bit tricky. The open time, the part where it's kind of still sticky and melty, isn't very long. I think with a larger hot glue gun, when it's higher temperature, it might be melting longer. Kind of the opposite problem with silicone. The silicone will stay open for a very long time. Some sort of sealant that kind of is in the middle would be nice. So somewhat related is sticky wax. So I used this in the last video. So this is wax. I think it's got some beeswax on it. When I was using it, I definitely smell a little bit of honey. But it's probably combined with some other waxes and melts at a relatively low temperature, like 100, 120 degrees C, so much less than the PLA. It will flow nicely, and when it's cooled down, it will become kind of sticky and hold things together. That's what I used when I originally put this mold together, and it worked okay. I think it's a little bit fiddly trying to get the wax down just right, and there's probably some learning curves there with the application technique. I actually wound up with a problem where it wasn't sealed completely. That may have been due to my geometry, or again, it may have been my technique, but I think it also speaks to kind of a general issue with these types of approaches where you really need it everywhere. This is true for both the hot glue as well as the silicone as well as the wax. If you don't have a good bead down that's nice and thick, potentially the plaster will find a way out. Another option I've been thinking about is using mechanical fasteners. So potentially you could use a bunch of these little spring clamps that I have laying around to basically clamp things together, or the bigger clamps I use for my coddle boards, or maybe even rubber bands. These are used to hold plaster molds together. The idea would be to basically press the pieces together such that they can't come apart. Another option on the mechanical side are these. These are threaded inserts. So these are tiny little brass pieces, and the idea is that you heat them up and press them into the 3D print into a little hole. These are threaded so they could then hold a bolt. And that's actually what I showed you in the beginning of the teaser. This is a few 3D printed parts, just like this. This is actually an earlier version. They have a bunch of holes, and the idea is that you can put the inserts in and then bolt everything together. One of the advantages of having holes in this is actually alignment, so the bolt and the insert can line up, so I don't have to worry about the orientation of the pieces. They will kind of naturally go to the right spot. The problem, as I showed in the beginning, is actually sealing. Because my 3D prints aren't perfect, there are actually small gaps when these are even pressed up tightly together. And while it may resist the flow of water, it definitely is not watertight. And I think that's a problem with most of these mechanical approaches. Because of the imperfections in the 3D print, we can hold it together with the mechanical fasteners, but we can't actually get a watertight seal or a plaster-tight seal. Those are a few of the options I've been thinking about, and there are probably a few more that I missed, but I suspect they all have similar drawbacks. They solve one problem well, and then they introduce another one. They may be strong, but they're bad at sealing, or they may seal very well, but then they're hard to take apart, etc., etc. So I think what we actually need is to combine the approaches together. We need to take a couple of these and put them together into one solution. Basically, that will let us combine the strengths of a couple of the approaches, and hopefully the drawbacks are then covered by the other piece. And that's what I want to do. So that's what this 3D print was an early test of. I wanted to, one, prove to myself that it wasn't actually watertight, and indeed it's not. But this gives us nice alignment and is very strong. It gives us a lot of mechanical strength. So I don't have to worry about the plaster kind of pushing it apart, and I can get the pieces aligned very well. The piece that's missing is sealing. So going back to the pieces, what I need is to be able to basically place some sort of sealant either here or in between where the screws go that will prevent the plaster from leaking out. The nice thing is that there's actually a bunch of different options to do that. Again, if you're patient, you could just put a silicone bead down here. That would work. You could potentially use wax again, maybe, I'm not sure, or hot glue. You could even use throwing clay or modeling clay to put a nice bead in here. So that was the key insight, and that's really what I want to test in this video here. So I put this together manually. There's no magic software yet. And these were some early prototypes, and I made a bigger version. So I have all these pieces here, and the idea is that these will somewhat mimic the outer shell for the plaster. So I have the bottom piece here, and then I have these pieces here that will go on the side. For the test, I don't have an inner mold. I actually want to have this full of liquid so that I can test to see if it leaks. As I mentioned, plaster is denser than water, so I want to basically put as much water in here as possible to see if it will leak out. By removing the inner mold, one, I made the test simpler, but I also then give me more water pressure, more water volume, so I have more static pressure to try and push out in the seams. So what I've done is I've added flanges to stick things together. So if we think about the inner ring, so these flanges here stick out, so I can bolt them together and press down. So that deals with the ring joint that we had before. I then also added flanges to the outside, like this. That will let me split the outer mold into several pieces, like I have here, and then bolt them together. You'll also notice this little lip here, and that's a recess that I put in on purpose. So the idea is to actually have intentionally a little gap on the outside, and the mating surface is the one on the inside. So I have a small contact patch that needs to seal tightly, and this gap here will basically act as a little bit of a spring, so I can have some compression between the pieces and suck them together. So that mechanical force and some sort of sealant together will hopefully hold these together tightly and in a waterproof way. The outer edge has a similar little lip. I think it's only like 1.5 millimeters, but just enough to be able to have a bit of a gap. If these were exactly flat surfaces that are trying to mate together, I think it would work less well because the area that I need to seal is much larger. And then finally, while I have printed all these holes in these pieces, I think it's actually flexible. Potentially you could just clamp this together or maybe tape it together and then seal it separately. Hopefully this flange approach is then relatively versatile and you can try different things. If this works, I can go ahead and add this flange into the software and have it created automatically. And by the way, I have a link in the description if you want to sign up for an early beta version of the software as well. All right, let's go ahead and assemble this. First, I need to put the threaded inserts in. You probably can't tell on camera, but these holes are actually slightly different size. So I've done this for M3 bolts and inserts. The hole for the insert is slightly bigger than the hole for the bolt. I've got my soldering iron here set off to the side. This is actually set at a very low temperature. It's actually only set for, I don't know, like 220, 225 C. Basically just enough to melt the PLA. I have not used these inserts a lot, but I got the ones that are designed for 3D printing in particular. There are others that are meant to be thermal set into other types of plastic. These are slightly cone shaped, so there's a narrow end and then a bigger end. The bigger end is the outside. The narrow end is the part that gets inserted into the 3D print. So this is hot, so be careful. So basically, I'll just pick it up with the tip and then put some gentle pressure down. You don't need to push very hard, it'll slowly melt. And then slide in. And I want to make sure it's below the surface and perpendicular to the surface, or at least as most perpendicular as I can get. That's the other reason this is slightly recessed, is that I noticed that sometimes the plastic will mushroom up just a little bit. That may also interfere with the seal and alignment in general. I kind of went on the safe is better than sorry side with these inserts, so I have a lot of them. If we wind up using these only for mechanical properties, we might be able to get away with less. But I figure at the very least they will be helpful for alignment. These inserts are also reusable in a couple different ways. So one is obviously it's a threaded hole, so I can screw and unscrew this multiple times. So if I want to reuse the molds, I can do that. Also, when you're done with the 3D printed parts, you can actually use a soldering iron and pull the insert out and reuse the insert. So for instance, the demo I showed in the black 3D print at the beginning, I actually reused those inserts a few times. I had popped them out of some early attempts and then put them back into new pieces. And I will probably, when I'm done with this, go ahead and reuse those inserts as well. All right, let me go ahead and speed through this. All right, there are all the inserts. There are 30 in total for this part, and that took maybe 10 minutes, so a little tedious, but not too bad. All right, next we need to start assembly, and to do that, we need to seal this. In thinking about sealing, there are several different options, as I mentioned. One I thought about was petroleum jelly, also have some plasticine modeling clay, and finally is regular old throw-in clay. I've used this to seal up some cottle boards, so it's actually been contaminated with some plaster. I think I'm going to go ahead and use the throwing clay. I'm not too sure it's the best option, but it's one that if you're a potter, you probably have access to. So let's go ahead and go with that. So I think my strategy is just basically go ahead and roll out a coil that I can put down on all of these mating surfaces. And this gap, as I said, is I think only 1.5 millimeters, so it doesn't need to be a very big coil. Make sure we overlap so there's no gaps. All right, and then we have an opposite face. I'm just going to squish these together. I'm going to cheat and use my drill. All right, that one is in. First, I just want to get a couple in and get it to a line. And that may be too much clay. We have a gap there. We'll see if it cinches up with more of the inserts. But let me get the other sides first. All right, and then you squish together. Same thing, I'll just get a couple screws in to get it to align. One side fell apart, so let me do it again. All right, there are all the sides, and we're getting some clay squished out in the middle, so I suspect that means we're gonna get a good seal, but we'll have to clean that up. So let me put in the rest of the bolts on the side. I got all the bolts in. I didn't get the bottom ones in. I need an extension for my drill, so I couldn't reach. However, that's where the bottom piece goes, so I think it'll be okay. And I do have some squeeze out on the inside, so I think I'm gonna go ahead and take a sponge and wipe that up real quick. Again, it doesn't matter for the test, but I wanna see if this is what I'm gonna do for real. Oh, that's a little bit better. And next we need to put in the stand-in for the ring on the bottom. So again, there's a step here, and that goes towards the mating surface. So screws will go down this way. So we'll need to put some clay around the outside here. Play around. And this will go on top. I got all the sides in, so I'll put in the last few. These threaded inserts can be stripped out, so you don't want to put too much torque on them. We got all the clay to squeeze out. So hopefully this now is mechanically tight and watertight. I'm seeing a little bit of deformation in this top ring here. I think it's probably the clay that's causing it to pivot a little bit. So that may be something to think a little bit about. Definitely got a lot of squeeze out, but I think we have too much clay in the middle here. Let's go ahead and do the same test as the opener and see if it works now. So I've got some water here. I may need some more. I'm gonna pour it down in. And so far, no leaks. Oh, we sprung one. Over here, I think it's actually coming through the 3D print. Put some petroleum jelly on here and see if I can get the seal up. All right, that is not what I was expecting to fail. So for this video, I went ahead and decreased the wall thickness. I was curious to see if I could print these a little bit thinner. And apparently the answer is no, I cannot. I also printed this on a very draft setting, and there were definitely some 3D printed artifacts that I wound up sanding down a little bit. But I'm guessing that also compromised the waterproofness of this. All right, what have we learned? Well, one is I need thicker walls. The ones I did originally for this pot seemed to be right, so I thought I could get by with something thinner, and the answer was no. Looks like the inserts are mechanically holding this together. That's good. I'm not sold on the clay as the sealant though. It's obviously readily available, but I had to compress it quite a bit to get it to squeeze together. So I think I'm gonna go ahead and reset and try this again. I wanna fix this 3D print, even though it's a test. I would like to make sure that's not leaking. Clearly it is now, and I think I want to revisit the clay. All right, so 2 steps forward, 1 back. I think we have at least identified what the challenges are, and I think we are partway towards a solution. So this was a good test. We definitely learned a few things, although some of them weren't what I expected. I was hoping to go ahead and incorporate these changes into my software so I could start making pots this way. However, it looks like there's a little bit more work to do. So let me go ahead and revert to the wall thickness and print these out again, and then we can see what other sealant options might work better and cause less stress on the 3D printed part. So stay tuned for that. That will be the next video. If you have any questions, comments, or ideas in this vein, let me know. Thanks.